In physics, there are two types of energy that we study: kinetic energy, which we've already learned about, and potential energy. Potential energy is stored energy that can be later transformed into kinetic energy as something moves. Usually, potential energy is stored due to an object's location. There are two types of potential energy we'll study, and those two types are gravitational potential energy and elastic potential energy. Gravitational potential energy is all about the object's position relative to some reference level, and it refers to the fact that an object could fall depending on where it is. Whereas elastic potential energy is potential energy associated with deformation, often dealing with springs, when a spring is stretched or compressed. We'll learn more about each of these two types, starting with gravitational potential energy. As I mentioned, gravitational potential energy is stored energy that is due to an object's height. When we calculate gravitational potential energy, we always need to define the reference level. The reference level is the level at which gravitational potential energy is zero. U sub g stands for gravitational potential energy. That capital U is the general symbol for potential energy. At the reference level, gravitational potential energy is zero because the height is zero. Gravitational potential energy then obviously depends on height. It also depends on gravity. That's where it got its name from. The equation for gravitational potential energy is mgh. M is mass, g is gravitational acceleration, 9.8 meters per second squared, and h is the height above the reference level. You'll notice there's no vector symbols, so we don't plug in negative 9.8, but it's possible for us to plug in a negative height. You would plug in a negative height if your object is located below the reference level. Again, just like kinetic energy, the unit for gravitational potential energy is joules. So let's see what some problems may look like with gravitational potential energy. In this first one, a boy is lifting a book from his desk to the bookshelf. It's asking what is the potential energy of the book relative to the desk. That tells me that the height of the desk is the reference level. So we're calculating gravitational potential energy with the equation mgh, and we're given that mass is 2.2 kilograms. G will always be 9.8 meters per second squared. Again, positive because there's no vector symbol. And then we need to figure out height. Height is always the distance above or below the reference level. The reference level is the desk, which we know is 0.8 meters high. The bookshelf is 2.1 meters high. That's the height above the floor, not above the desk. So we need to calculate h, the height above the desk. To do that, we'll take 2.1 minus 0.8 to get a height of 1.3 meters. 2.2 times 9.8 times 1.3 gives us a potential energy of 28.03 joules. Let's move on to another example problem that's slightly different from this one. In this one, a warehouse worker is picking up a box from the floor, setting it on a table, sliding it along that table, and then lowering it back down to the floor. We want to know the changes in the energy of the box for each step, and we want to know how the total energy of the box changes. Well, let's name these steps. Let's say that when the worker picks up the box from the floor and sets it on the table, that is step A. Step B is as he slides it along the table, and step C is when he's lowering it back down to the ground. We'll calculate the energy for each of these steps. One thing that makes this problem different is that there is not a clearly defined reference level. When this happens, it's up to you to choose where the reference level is. You always want to choose a level that's convenient. Typically, that's the lowest the object could go. In this case, the lowest the object could go is the ground. So we will make our reference level to be the ground. So in calculating the gravitational potential energy, as the worker moves the box from the ground, our reference level, to the table, we'll use the equation mgh, where m is the mass of the box, 10.1 kilograms, g is 9.8 meters per second squared, and h is the height above the reference level, 1.1 meters in this case, because that's the height of the table. 10.1 times 9.8 times 1.1 gives me a potential energy of 108.9 joules. So as this box is set on the table, it has 108.9 joules. Then this box is slid across the table at a constant velocity. If it's slid across the table at a constant velocity, its kinetic energy is not changing, and its height is not changing. Therefore, as it moves across the table, it has no change in energy. In part C, the change in energy is the change in potential energy. Change is always calculated by doing final minus initial. The box is lifted from the table to the floor. If it ends on the floor, it's ending at our reference level, so the height is 0. Therefore, it has no gravitational potential energy there. So the change in energy is simply the negative initial gravitational potential energy. That's how much energy it had when it was on the table. And we already know that number. That number is 108.9 joules. So in this portion, where the worker is moving the box from the table down to the floor, the box loses 108.9 joules. So the change is negative. Overall, if we add all three changes in energy, we find that the total change in energy is 0. Energy is conserved, we say with this, because the energy doesn't change from the initial to final point. One last example problem. In this one, a rock climber first climbs 45 meters up to the top of a quarry, then descends 85 meters from the top to the bottom of the quarry. It tells you the initial height is the reference level. That means that his height before he climbs 45 meters is the reference level. Let's draw a picture of that. Here's kind of my cliff, my quarry. Here is where the hiker starts. He goes up 45 meters to the top and then goes down 85 meters. This dashed line represents my reference level. This is a problem I'd like you to try on your own and bring to class tomorrow. Again, pay attention to where that reference level is when you're determining what h to plug into the equation.